So let's say you have a region here. Now this is type 1, type 2. I don't know. I mean, it's whatever. I've never referred to these as type 1s and type 2s. I don't know what the value that is, but let's take a look at this region here. So each of these three regions, what do they have in common? They're basically defined this way. They're defined by sets x, y, where the x is defined on an interval, and the y then is defined as between functions of x. Okay? So basically, the bounds on the x are constant, and the bounds on the y are variable. So you can see there's a couple different scenarios here. But here's how you want to think of this double integral. Is we're going to, the outermost integral here is going to be constants. We're going to be chopping up the x-axis from a to b. And for a fixed x, what's the y run between? Well, I like to run from bottom to top. And that's how we kind of fill out this region. So I was doing some of this yesterday and today when we were filling out those rectangles, but that's how I like to think of it. There's like a sweeping action. For a fixed x from a to b, y is going to run from g1 to g2, and that's how we fill out that region. If you've got the reverse situation happening, in other words, if your region R can be described as a set of points x, y, where the y is constant, but the x is between variable bounds, then what you can do is you can come in here and chop up the y-axis between constants c and d, and then for a fixed y, see what the x is running between. Once again, you're going to fill this out going from right to left. Or excuse me, left to right. I drew it the right way, I said it the wrong way. Okay? But the key thing in both of these is to realize the outermost integral will always have constant bounds. So if it's dx dy, we're going from the left to the right constant, and then from the bottom to top curve. If we're in this type of region, it's a bottom to top constant, left to right curve. So whatever's on the bottom, whatever the lower limit is, it's always the smaller. So if you're looking at x's and y's, the smaller of the two things is on the left. If you're looking at x's, the smaller of the two things is always on the left. If you're looking at y's, the smaller of the two things is always on the bottom. Okay? So we'll sketch the region here. We do got a couple minutes. Sketch the region over this integral is being evaluated and evaluate the integral. So here we've got constant bounds on the x. That's the outermost integral. I think I was using x as red though. There we go. There. So x is going from 0 to 1. So there's 0 to 1. So we'll call that 0 to 1. And for a fixed x, what's the y run between? The y runs between y equals 0 and y equals x squared. So y equals 0, aka the x-axis. Y equals x squared, that's your nice friendly parabola. And so this is the region that we're sweeping out. Okay? So that's our region R. But do you see how you can take this and then build the region from that? That's the skill you're going to want to need here. Okay. Now in this particular one, you're integrating with respect to y first, which means you treat x as a constant. You can slip that x out and just integrate this. We don't have time to go through it. I'll let you finish that up for your homework then. You can go ahead. Integrate that one. Get the x in there. And then there's an x out front waiting for you with the u substitution. Okay, so see if you can get this to work out as part of your homework for tomorrow. Let's take a look at example 2. What goes wrong when trying to evaluate this integral? So if we try to evaluate this integral as an iterated integral as is, remember we always start from the inside out. So I'd be trying to integrate 2x to 2 sine of y squared dy. And even though sine of y squared is continuous, we don't have a very nice way of writing the antiderivative for this. Okay. You can try all your basic techniques you learned back in Calc 2 or the AP Calc. This one just isn't gonna work. All right. You could always bust out your friend the Maclaurin series and get a power series representation for that, or maybe use some advanced functions, but that's just not going to work. So this is an example of where reversing the order of integration not only is convenient, but it'll actually let you do it. So sketch the region over which the integral is being evaluated. So that's always a good idea here. This will kind of review the concept here of sweeping motion. So here's the xy plane. X is going from a constant 0 to a constant 1. So there's 0, there's x equals 0, x equals 1. And we're chopping up the x-axis from 0 to 1. And for a fixed x, the y is running between y equals 2x and y equals 2. So y equals 2x would be the bottom curve here. So there's y equals 2x up to y equals 2. And sure enough, they meet there at the point 1, 2. And so for a fixed x between 0 and 1, we're letting the y run between the line 2x and the line 2. And so that is what's sweeping out our region R. Okay. Any questions on how we're obtaining the region from the limits on the integral? So the way we're going to try to evaluate this then is to reverse the order of the integral, of the integration. So I'll just put that down here. The integrand is going to stay the same. I'm integrating the same function. I'm just going to use Fubini's theorem and say, okay, I'm just going to reverse the order of that integration. So if I'm integrating with the order dx dy, I'm chopping up the y-axis from a constant 0 to a constant 2. And now for a fixed y, I have to figure out what the x runs between. For this region, I'm always starting on the y-axis, aka x equals 0. So I'm starting at x equals 0. And I'm always going to finish up at this line. So this line, the way I've expressed it, I have y as a function of x. But for a fixed y, I need to know how far the x goes. That means I need to express this x as a function of y. So if y equals 2x, then what's x going to be as a function of y? Yeah, good, y over 2. All right. Any questions on getting the limits of the integral, switching the order? I highly recommend you draw the region and you kind of follow this idea of chopping up the one and then sweeping to get the other one. So what's the advantage of this integral? In this integral, I'm integrating with respect to x first. And as far as x is concerned, this entire thing is just a what? It's just a constant, right? So if I wanted to, I could even factor it out of the integral if I wanted. I could even factor it out. And now I'm just going to integrate dx from 0 to y over 2. So you integrate 1 dx, that just gives you x. Evaluated from x equals 0 to x equals y over 2. And so you're just going to get the integral from 0 to 2 sine of y squared. And then this is going to turn out to just be y over 2 dy. So if I rearrange this, I can factor that half out. 0 to 2 y sine of y squared dy. And you see why this is nicer? Because what technique could you use to evaluate this integral? Yeah, you do a basic u sub, or depending on how many of these sorts of things you've done, you can just get the antiderivative this way. If you take the derivative, you'd have a 2y come out. You just have 1y, so that would be a quarter is minus cosine y squared from y equals 0 to y equals 2. So let's double check that. Derivative of cosine of something is minus sine of that thing, so the minus will take care of that. Times derivative of the inside, 2y, boom. Right? So minus a quarter cosine of 4 minus a quarter of 1. So 1 minus cosine of 4 over 4 looks to be our answer. So in this particular case, if you switch the order of integration, that'll help you out. Now let me fire up Desmos here. I tested some double integrals yesterday. Let's see if we can coerce Desmos to help us with this one. We can check the numerical answer. So on Desmos, so if you had me for the other calc sequence, we use Desmos all the time. So Desmos, I'm just going to put integral 0 to 1, integral 2x to x, or 2, and sine of y squared dy dx comes up with that. We had 1 minus the cosine of 4 over 4. There you go. So you can actually check your answers numerically on Desmos. Okay. Area using a double integral. So let's say you were wanting to figure out the area of this region here. They call it D for, well, probably D for domain. Then back in Calc 1 or AP Calc, you would integrate from left to right, top curve minus bottom curve. Okay? So what you could do is you could think of this as integrating 1 dy from the lower curve to the upper curve. You integrate dy, you get y, plug in the top curve, subtract off, plug in the bottom curve, and analogously you could do the same thing. So mechanically, this is how you can get to the following result. If you want the area of R, you just take a double integral over R of 1 dA. All right? So mechanically, that's why it happens. If you actually just go in and think about what you're doing here, you've got this region R, and you're chopping it up into these little rectangular pieces, and you're looking at the area of all these individual little pieces. All you're doing is adding up all these little parts of area, and as long as you've got your mesh shrinking to infinitely small rectangles, You're just basically adding up the area of R. You've chopped it up into a bunch of pieces. Now you're adding them all back together again. Okay, so that's your area. But I do want to point out how this is very, very analogous. If I wanted the length of the interval AB, I could just integrate over the interval 1 dx. That's the integral from A to B, 1 dx. That would give you the length of AB. So once again, when you integrate 1 over your domain, you're somehow getting the natural measure of that domain, whether it's the length of the integral or the area of a region. So let R be the region bounded by these curves, y equals root x, y equals 6 minus x in the x-axis. Set up iterated integrals with order dy dx to calculate the area of R. Set up these iterate integrals with order dx dy to calculate the area of R. So this is really just an exercise in setting these things up. If you had me for Calc 1, this region will look familiar because I used it back in the day. So let's try to sketch it here. We got y equals root x, y equals 6 minus x in the x-axis. The x-axis, aka y equals what? 0. Now, if you don't remember these things, I suppose you could always fire up Desmos to do it. But root x, that looks like half a parabola. Looks like that. 6 minus x, there's your line. And then y equals 0, that's your x-axis. Whoops. So if I'm looking at the area that's bounded by all of these things, then it's going to be this character here. So that's going to be our region R. Now I know that I can calculate the area of R by doing a double integral of 1 dA, and they just ask us to set up the integrals in the different orders, so we can kind of compare and contrast the complexity of these things. So let's say we wanted to go dy dx. So if I wanted to do the dy dx, I'd be chopping up the x-axis between constant bounds. So I'd have to figure out what these points are. So this point is 0. This point is where the 6 minus x crosses the x-axis. So this would be x equals what? 6. And then what I'd have to do is, for a fixed x, figure out what functions of y, or what y runs between. And you notice the bottom here is always the y equals 0. So y equals 0 is always the bottom, but the top changes. So for these x's, the curve that's on the top is square root x. For these x's, the curve that's on the top is 6 minus x. So I'm going to have to break things up at whatever this point is. And how would I figure out what this point is? That would be where these two graphs cross. So how could I figure that out? Yeah, you have to solve that equation. Yeah. Yep. And you can go through that. You'll get two answers. Only one of them works. We'll get x equals 4 for that. So I'll save the algebra for that. So do you see why I'm going to need two integrals here? The first integral, x is going to go from 0 to 4. And then the y goes from y equals 0 to y equals root x. And then I'll use the properties of the double integral. Since the overlap here is just going to be a vertical line that's got no area, I would add to that. X picks up, 4 goes to 6. And then 0 up to 6 minus x. That would be 1 dy dx. So you would need to add to those integrals to get your area. Any questions on how we're getting the limits of the integral? This is the key skill you're going to need here, is being able to set up these regions and then visualize what's happening. Now let's look at what would happen if I looked at it the other way. If I integrated dx dy. So once again, the outermost limit of the integral is going to always be constants. So here I'd be taking this region and projecting it over to the y-axis and seeing what would get chopped up. So here I know that the y equals 0 is down here. If I know that this is x equals 4, then I should get the same y if I plug it into either one of these things. So I plug 4 and I'm going to get 2 out of both of those. So I'm going to erase this for a second. I'll put a 2 there. I still want y equals root x here. And now I'm going to be chopping up the y-axis. And for a fixed y, I need to know what the x runs between. So for a fixed y, x is going to start here and go from left to right. Now for us, the leftmost curve is always the same, and the rightmost curve is always the same. But what I need is to know what x is in terms of y. In other words, if I pick y equals 1, I need to be able to figure out what the x is going to run between. And so just like in the last example, I need to recast these things. If y equals square root of x, I need to solve this, x in terms of y. And so if y equals root x, x is going to be what? Yeah, y squared. And if y equals 6 minus x, that means x is going to be what? 6 minus y. And I'm going from left to right, so I would go from y squared. Y would go from 0 to 2. And then for a fixed y, the x goes from left to right. X equals y squared to x equals 6 minus y. All right. Integrate the x, you'll get a function of y, and then integrate the y. So you can see here, this would be a much easier integral to evaluate to get the area, as opposed to integrating these two individual ones and adding them together. All right. So when you're setting out to set this up, it pays to explore the different orders of integration to see what's gonna work best. Any questions on getting the limits here? So once again, when you go to set these double integrals up, your goal is to get one that looks like this or get one that looks like this. Be mindful of the order and just think about what's going on there. And I'll leave it to you to go through and get your the actual value here. And since it's area, it'd be units cubed, or units squared rather. All right, it's time to get back to the volume problem. So when we first kind of started double integrals Monday, we looked at the area problem in Calc 1 and then generalized it. Instead of looking at the area between the graph of a function of a single variable and the x-axis, we said, what if we tried to figure out the volume between the graph of a function of two variables, a surface, and the xy plane? And so here's the big idea. Volume is going to be a double integral over the base times the height. Now, what's the height function? If your base is going to be in the xy plane, the height's going to be determined by the z. And you would want to project the solid into the xy plane, and GeoGebra is going to help us do that nicely. And then integrate. That would be your base, and then vice versa, or not vice versa, but then you just sort of permute the letters around, depending on where you want the base to be. So let's take a look at this example. Consider the solid bounded by the plane 2x plus y plus 3z equals 6 in the first octant. So there's a sketch of the situation. Set up an iterated integral with order dy dx, which would compute the volume of the solid. All right. So when they say order dy dx, this is telling us that they want the base in the xy plane. All right. So my volume is going to be a double integral, once again, over the base of the height dA. So if they're saying dy dx, that's our dA. Base is in the xy plane, so they're telling us that the height here is going to be what variable? The z. Okay. So looking back at this plane here, we've got 2x plus y plus 3z is 6. The height then, I'm going to solve for z. And so what would you get when you solve for z here? Yeah, 6 minus 2x minus y all over 3. So now for the base, I need to project this solid into the xy plane. Okay. And also we're in the first octant. All right. So the first octant, remember, x is bigger than or equal to 0, y is bigger than or equal to 0, and z is bigger than or equal to 0. All right. So we can do this algebraically, and then we can use GeoGebra to check graphically. So to project into the xy plane, we're zeroing out the z. So let's go ahead and try to start sketching this now. So we'll look at the base here. X's and y's. So x bigger than 0, y bigger than 0, that tells us we're going to be in the first what? Quadrant. So here, what color do we, well, I guess we'll use blue for the base. So here's those things there. There's the y equals 0, and here's the x equals 0. We're going to be over here somewhere. Now if I put z equals 0, if I put z equals 0, remember we had a name for this. This was called the what? You remember? This goes back to like week 2. Projection, we called it the trace. Yeah, it was the xy trace. That's the word we use. But projection works too. So 2x plus y is 6. That's totally not right. Hold on. So 2x plus y is 6. And if we want the z to be bigger than 0, I would have this bigger than or equal to 0. So I would actually get 2x plus y less than or equal to 6. So I would be getting this for my region R. So we'd have an x-intercept at 3, y-intercept at 6, and then of course we got the zeros there. So there's what R should be. Okay. Any questions on how the algebra can be used to help us figure out what the base is? This is they can get more intimidating than this, but let's show you how we can use GeoGebra. Now, I haven't found a good way to do this on Desmos. I mean, I would take that as a project if you can show us all the amazing things you can do with Desmos so as to avoid GeoGebra. So here's GeoGebra. Let's see how it's behaving today. GeoGebra usually handles planes pretty well without solving for Z. There's that plane. Okay. And then we'll do x equals 0, y equals 0, z equals 0. Well, z equals 0 we don't need. Let's put those in there. And then we'll go to Tools and we'll look at Intersect Surfaces. And we'll just click the surfaces here. There we go. We will put z equals 0 in there. Intersect surfaces. There we go. And now if we look at come on, GeoGebra, please. Too far. Here we go. Well, there we go. So here's the here's the x, here's the y, there's the region R. What's nice about GeoGebra is when you click Intersect Surfaces, it'll actually show you the intersection, and so there you can see there's our region R. There's the 6, there's the 3, there's the 0. Okay, so that's how you can use GeoGebra to help you figure out what that is. So this is the base of our solid. Okay, it's the base. And then we're going from the XY plane up to that other plane, and so that's our height. All right. So the volume is the double integral over the base of the height dA. So that's a double integral. The height is that z we found there, 6 minus 2x minus y over 3. And then for dA, at this stage in the game, we have two options. We can either do a dx dy, or we can do a dy dx. The shape here is a triangle. So do you want to do dx dy or dy dx? Because whichever one you pick to do together in class, I'll have you do it or wait, did they tell us which one they wanted us to do? They told us dy dx. Okay, fine. They told us dy dx. So that means when I go into my region here, I'm chopping up the x's. So the x's are going to have constant bounds between 0 and 3. And now for a fixed x, I have to determine what the y runs between. So as I go through the interval 0 to 3, I'm looking at the y's here. And we've got the same function down here the whole time. That's our y equals 0. So that's the bottom function the whole time. And then I need to go to the top function. The top function we know is this trace. 2x plus y is 6. But for a fixed x, I need to know what that y value is going to be, which means I got to solve this for y. And so if I look at y as a function of x, what's the equation of this line? Y equals what? Yeah, 6 minus 2x. And then you'd go through and do your integration. You'd integrate the inside, get a big old function of x, and integrate the outside. This is a lot like the one I had you do for homework, I think, Monday night. But whatever number you get here, remember, the way we're interpreting this integral is that this is a height function, and this is an area. So whatever you get would be units cubed for volume. Okay. All right, set up an iterated integral with order dy dz, which would compute the volume of the solid. So once again, when they give you the order dy dz, this is telling you that they want the base in the yz plane, which means the height would be given by what variable? X. And so we've got the plane uh, 2x plus y plus 3z is 6. So to get the height function, I would solve for x in terms of y and z. So I'd subtract off the y and the 3z and divide everything by 2. That would be the height. So to figure out the base, I'd have to project this thing into the yz plane. So we'll look at the yz plane. And I can pretty much do the same sorts of things we did earlier. If I'm projecting into the yz plane, the x would be 0. If I plug in x equals 0, that gives us the yz trace. Y plus 3z is 6. Y would have to be bigger than or equal to 0. Z is bigger than or equal to 0. X would be bigger than or equal to 0, which would mean y plus 3z is less than or equal to 6. You would get the same kind of setup we had before. That would be our region R. And what's nice about this is if you've already put stuff into GeoGebra and invested that time, we can now just rotate this around, project down the positive x-axis. Come on. Here we go. It's almost there. There we go. You see, that's the YZ plane, and there's our region R. You follow? So GeoGebra can be really helpful. You plug in all the equations, and then you just look at the intersections between them all. They're looking at the order dy dx or dy dz for this. So once again, volume, double integral of the base, height dA. They want dy dz for the dA. So the height we know 6 minus y minus 3z over 2. And now let's look at setting up the integral over the base with dy dz. So dz is the outermost limit there, so we'd be chopping the z-axis up from z equals 0 to z equals 2. And now for a fixed z, I've got to figure out what the y is running between. So as I start off here, I'm always starting off from the z-axis, aka y equals what? Zero. And then I'm going over to this. Once again, I need y as a function of z. So this would be y equals. So for a fixed z, I need to know what the y runs between. So I have to plug a z into here. I need to solve for y. So y would be what? 6 minus 3z. There you go. And once again, you can go off, do your calculations, and your final answer be units cubed. All right? And you should get the same number you got from part 1. And we should have enough time for this last example here. We're going to project things into the xz plane, which means that the height is going to be given by what? The y. So I go back to my plane here. I've got 2x plus y plus 3z is 6. So the height y is going to be 6 minus 2x minus 3z. So the base is going to be in the xz plane. Looking at the xz trace, 0 out the y, 2x plus 3z is 6. I got an x-intercept of 3, a z-intercept of 2. Going through the usual analysis, we're going to pick up the x equals 0, the z equals 0, and 2x plus 3z less than or equal to 0. There's our triangle, which we could verify on GeoGebra. What would the volume be? They want dx dz. We'll go ahead and put our height in there. 6 minus 2x minus 3z. If they want dx dz, once again I'm going to be going in and chopping up the z-axis. From z equals 0 to z equals 2. Now for a fixed z, I got to figure out what the x is running between. So to sweep out this region, the x is always starting over here, which is x equals what? 0. And then I got to get over to this line. For a fixed z, I got to figure out what the x is. So if I plugged a z in, I'd have to solve for x. And what would x be then? 6 minus 3z all over 2. And if you go through and your iterated integrals, you should get the same number, which apparently is 6 for all of these. Okay. And since this forms a tetrahedron, if you look at this, this forms a tetrahedron, 6, 2, and 3. There's a nice little formula for the volume of a tetrahedron you can apply to get the answer 6. Okay. All right. Well, we do have a few minutes. We should be able to get through this one. Maybe not. We'll save this. We'll save these next ones for tomorrow. We got a whole other day set aside. It's only Wednesday. Sometimes I think it's Thursday, but it's only Wednesday. So instead of getting in the middle of something and then having to shut out early, we'll go ahead and cut out now. Tomorrow, then we'll finish up looking at 16.2. And then what we'll do on Friday is we'll just review polar coordinates. All right. So I'll show you how I like to think about polar coordinates in terms of the sweeping motions, the sweep out areas, and then that'll give us another means to describe bases of these solids, right? If we have like circles and stuff, we don't want to be using rectangular coordinates for that. We want to be using polar. Okay? So as always, folks, I appreciate you tuning in. Hope you get out and enjoy the weather today, and we'll see you here tomorrow.